The fluids are now moving. What do we call that?
Fluid dynamics.
Fluid dynamics. Yes. All of you engineers should know the difference between statics and dynamics. Now, if you sum up all the forces, they don't necessarily add to zero. Okay? And torques. Yeah. Okay, so hydrodynamics, that means we have to start with the simple model, which means ideal fluids, which means somewhat unrealistic, but realistic enough for starting out. Okay? So ideal fluids are incompressible. And what do we mean by incompressible?
Can't change its density.
Okay, you can't change the volume easily, okay? Non-viscous, okay? Name something that's viscous. Maple syrup. You guys have seen it. You guys have seen that Super Troopers where they chug the maple syrup. Yeah, that is viscous. And you know what? Viscosity was an issue there because if you watch the behind the scenes, which of course you all have, on Super Troopers, they tried to do it with colored water and it just didn't look right because water does not have the same viscosity as syrup. So they ended up actually chugging syrup, which is just disgusting. Okay. And
on the Leno show.
really? Flow is steady. What do we mean by that? Oh, yes.
Just fun fact about like commercials. If you ever see like a commercial with cereal and they're pouring milk, it's not milk. It's actually Elmer's glue watered down. So that way it does like the weird globby look.
Ooh.
Milk doesn't do that at all. It's too liquidy.
Don't drink this. Just gonna throw that out there. Do a quick glue on your cereal. Wow, that is. Oh yeah, all like food photography is a whole like industry to itself. But so flow is steady. What do you mean by flow is steady? On that note.
Constant.
Yes.
There's no air bubbles in there, none of that science.
Science. It mostly means that everything's flowing at about the same speed. Okay, so
And
flow
not
is
crossing
steady.
over.
Yeah. Wait, what?
And not crossing over.
And not crossing over, so mostly straight line vectors, okay? And then flow is laminar, which just basically means non-turbulent. Yes?
Flow is steady, meaning no acceleration, or
Oh, yeah, we do use steady to mean that. Most of these problems we're doing constant velocity, but it doesn't necessarily mean constant velocity. Let me double check on that, but that is a good question.
I hope not.
Flow is laminar, which just means non-turbulent. Turbulence is the thing that knocks your drink over on an airplane. That means, let's actually here. Laminar, turbulence, okay? Low viscosity, high viscosity. We have some video-y things to look at that. So this is laminar flow. Oops, you can't even see it. Like it's moving.
Is it?
No, that's moving.
Yeah.
Okay. See, it's hard to tell if it's moving because it barely gets perturbed. But you can see, this is moving, but it looks like just a smooth, straight line. Yes?
So, have you ever seen those things that you put in your drinks? They're like Mios, whatever, like little squeeze bottles, and then they hit the water, disperse? Is that turbulent?
Yes, this is turbulent flow.
Okay.
Like that. Okay. So, yes, the Mios situation. So turbulent, basically, just the visually laminar flow is this nice smooth flow where you don't have dispersal out, right? It's all in one direction. It's all pretty uniform. It looks like the previous thing. Yes.
That's in a liquid, right?
Yeah, this is a liquid in another liquid. Is it? Okay. Okay. Yeah. So this is what turbulent flow looks like. Apparently, I didn't loop it, so. But yeah, turbulent flow is when you see a stream flowing and you see all those little whirls and whirlpools and ripples. That's turbulent flow. Laminar flow would just be like a nice smooth channel. Okay. Yes. All right. Cool. Viscosity. Low viscosity looks like that. High viscosity is more like. Like corn syrup has high viscosity, maple syrup has higher viscosity, ketchup has a pretty high viscosity. Fun fact though, ketchup is a non-Newtonian fluid.
Is it?
Yeah. We're not going to use ketchup in any of our problems. So Newtonian fluids are like these ones that behave nicely with the equations we're going to use. Non-Newtonian fluids have these weird things have you ever used silly putty?
Or cornstarch and water.
Yeah, cornstarch and water, that stuff you call oobleck. Those are all forces, so like, look, most things when you apply a force this way, the compression happens this way and it like reacts in the same way. So, do you guys know about the stress tensor? Did we talk about that? So like the diagonal stuff is like, that means, 1-to-1, if you have a force this way, it compresses this way, right? Non-Newtonian means you apply a force this way and stuff happens in like the other planes. Okay, so for instance, like you hit silly putty with a hammer, it changes the material like properties of the silly putty like in the other directions. So blood and ketchup are also non-Newtonian fluids. So depending on how you pour them, it changes the like flow and viscosity. It's crazy. Anyway, we're not going to talk about that. If you're interested in that kind of fluids, that is some upper division fluid stuff. Okay, or if you're interested in cornstarch and water, you can do that at home. You don't even have to take fluid dynamics, okay? But yeah, all of the non-Newtonian fluids behave strangely and do not nicely obey the fluid dynamics equations we're about to talk about. But there are cool things that happen out there. So if you like that, you can take like more advanced fluids, or I think material science deals with this a little bit. So I honestly don't know what's in material science. I think they like blue in material science, and maybe
they're smelling.
Doesn't the velocity have to
Sniffing glue.
change?
What?
Doesn't the velocity have to change?
What do you mean?
Class, yeah.
Oh, for fluid dynamics?
Yeah, for
Yeah, I was confused by what we mean. I have to look up what we mean by steady,
I
because
think
in
it-
physics sometimes steady means constant velocity, and sometimes steady means other stuff. So we don't have steady is one of those words that doesn't have a precise definition in physics. So
This is
I'm
what
gonna double
happens when
check.
you double up on shit and get lazy.
All right. Calm down.
You start using the same variable more than
Tyler
once.
is going to single-handedly fix all the nomenclature problems in
Right.
physics. I'm very excited for him.
Nomenclature,
So
right?
that's what everybody. That's the sexy part of science, right? Nomenclature.
Nomenclature.
So let's talk about the continuity equation. The basis of the continuity equation is flow is always conserved. Now this is a lot like what we talked about in, how many of you have not taken Physics 200?
I don't
Just
remember.
one of you.
I don't
Okay.
remember if it's
You were there though.
I
I
was there,
remember.
yeah.
You were
Technically you did.
I
Okay.
think it was absent though.
Emotionally absent from Physics 200.
Mentally checked out.
So remember, what do we know about current?
But what? Current?
It's
Electrical or water?
Yeah.
It's
Electric.
It's I.
It's I.
It's measured amps.
If you have, when we're talking about current flow, if you pick a junction, what do we know about the current in versus the current out?
Oh,
same.
Yeah, the current in
Same.
has to equal the current out, and that's because charge is conserved. You can't magically make charge appear or disappear, okay? So charge conservation leads to the fact that current flow, so the flow of charge has to be the same at each point, okay? So anything that goes in has to come out. The same concept is true for the continuity equation, but instead of moving charges, we're moving like molecules in a fluid, okay? So the flow rate has to be the same at each point as long as you don't lose or gain the fluid, okay? So flow rate is called Q, although we very seldom actually use it, okay? So the volume flow rate is constant. That would be volume divided by time. Okay, so how much fluid passes a particular point in a particular time in volume. Okay, that's flow rate. Now, how would you write Q? How do you get something in meters cubed divided by seconds? It says
Velocity times area.
yeah, it's velocity times area. Because remember, velocity is in
Meters
meters per second. Area is in
squared.
meters squared. So that gives you volume per time. Okay, and we write it, you could also figure out volume per time, but usually we already have velocity and cross-sectional area. These are just more useful variables. So the Q is velocity times area. Well, it's mostly speed times area, but it's not, we're not treating it as a vector if you want to be real precise. What that means is, if you have a smaller area, if you change the area to be smaller, the cross-sectional area, you get a larger velocity. Now, the basic premise of this is, let's say you're watering your lawn, okay? You just have a hose, and you want to spray something that's on the other side of the yard. What do?
Capping it off.
You cover it with your thumb. In physics, what are you doing?
You're
reducing your area.
Changing
You're
areas.
reducing your cross-sectional area, but you are keeping the same flow rate because you haven't adjusted the tap. Okay, so same flow rate, and that means you are increasing the velocity. Okay, to maintain the same flow rate. So that's the continuity equation, guys. That's it. Okay. All right. So we're gonna actually do that as a problem. Take about
There it is.
5 to 10 minutes, and you get to remember how to do kinematics. And
So this problem is pretty fun because it brings us back to projectile motion, which is the very beginning of mechanics. And so we're going to use projectile motion to figure out our velocity, and then we're going to use the continuity equation to transform that velocity under the new conditions. So just for some context, you start out with a hose, and you have water flowing out of the hose, and it follows a trajectory where we know it falls 1 meter, and then it goes over 0.3 meters, and then at some later time you put your finger over the hose so that we're going to make this really stupid assumption, but whatever, it's fine, that this gets basically much smaller, so, and it's still circular for some reason. But when you do that, you're expecting the water to go kind of a lot farther. It's still going to fall 1 meter, but now we want to know what this new delta x is. Okay, so in order to do that, we're going to first solve this first projectile motion equation for the speed. Now remember, projectile motion, we have these equations for delta x and delta y, and the thing that is common is the time. So delta y is equal to, so first off, do we have any component of velocity in the y direction? Not really, right? So we could see that the velocity here is all in the x direction, and the velocity here should be bigger, but still in the x direction. So this is usually v naught y t plus 1/2 a t squared, but we know this component's going to go away. We also have the x direction, and delta x is much simpler. It's just going to be v naught x t. So we use this equation over here to find the time, and then we plug it in over here to find the velocity, and we'll get started. So in this case, our time is going to be 2 delta y divided by g square root. So that's going to be square root of 2 times 1 meter divided by 9.8 meters per second squared. Okay, now there's some negative things here. We're not going to get into too much detail, but basically delta y and g are both negative and it cancels, so I've just sort of glossed over that. This is going to give us 0.452 seconds. It gives us another answer too, which is negative, but remember, time isn't really so much of a negative, so we're going to ignore that one. Then we plug this in, we solve for v naught x, that's going to be delta x over t. So that's 0.3 meters divided by 0.452 seconds, and we're going to get 0.664 meters per second. So this is our first speed, right? We're going to call this one, we'll rewrite it as v1. And when we talk about our continuity equation, that's a1 v1 is equal to a2 v2, where a is the area. Now we want to solve for v2, so that's going to be a2 over a1 times v2. We found v2. We can find the areas because remember, this is going to be pi r squared because we are considering both of these things to be circles. So pi r1 squared, and this is going to be pi r2 squared. So this is pi a2, that's going to give us, that's going to be 0.005, I believe. Yeah, 0.005. meters squared, and then this is 1 centimeter, so 0.01 meters squared times 0.664 meters per second. These should cancel. You plug in your stuff, and you get 2.56 meters per second. Now, just for a check, right, this is now our V2, and when you put your finger over the hose, do you expect the water to flow faster or slower? Well, once you decrease the area, the continuity equation, this guy, continuity equation, says that as you decrease the area, you have to decrease the speed, because area times speed is the flow rate, and that must remain constant. That's conserved. It's just like how current is conserved with the junction law. So, now that we have our new speed, we can go back. Remember, the water, because it's falling in the vertical direction, it's always going to take 4.52 seconds to fall 1 meter, okay? What changes is the distance in the x direction, because remember, the components in the x and y direction work independently. So we can still solve. If you look at our delta y equation, none of those variables have changed. It's still 1 meter. It's still 9.8 meters per second squared. And since we don't have any velocity in the y direction, this equation stays exactly the same as it was at the beginning. So all we need to do to get delta x is plug into this other equation, where now we have V2 times t. And we use the same t because, remember, it shouldn't change. Okay? So V2 is 2.56 meters per second. It's this faster speed. And then we have 0.452 seconds. So when we plug this in, we get 1.16 meters. So that's this distance. That's going to give us 1.16 meters. So it's going to travel quite a bit farther because it's moving faster coming out of the hose. So we're going to highlight that, and that's that distance there. So we've gone from 0.3 meters over here to over a meter. And hopefully that makes some sense.
It's just, so but one thing you'll notice about this class, this might be the easiest class mathematically, but it does bring in a lot of old stuff, so you'll feel some like creaking as we talk about stuff from 190, a little bit of stuff from 200. We talk about energy and force still. Like you'll see in the buoyancy problems, you still are drawing force diagrams. So it's all coming together, or not.
Or not.
As the case may be. Okay. So this guy, Bernoulli, sweet hair. Okay. So this is Bernoulli's equation. So it's basically what does this equation look like?
Hydrostatic or hydro pressure.
Think back farther to like 190.
It's like
Yeah, 1/2 mv squared. What was that?
It looks like work.
Oh.
Kinetic energy, right? And this rho gy, what does that look like?
It looks like mass. It looks like mass. 1/2 mass times velocity squared.
It looks like mgy, right? What's mgy?
That's work.
That is gravitational potential energy. So this is basically just an energy equation, okay? All we've really done is we've swapped out things that used to be mass, now they're density. So we're just dividing the energy equation by volume to deal with flow, okay? The only thing that's really different is pressure, but think about it. If you divide work as a type of energy, right, that's force times distance. If you divide that by area, or volume, right, force times distance divided by volume becomes force over area, which is pressure. So if you divide through our conservation of energy equation, right, kinetic and potential and work, okay, so that's the whole conservation of energy equation, you get Bernoulli's equation. It is not new. This is just conservation of energy applied to fluids, okay? So this is your gravitational component. This is your kinetic energy component. This is just any external work, which sometimes comes from outside molecules pressing on you. Okay? So this is exactly the same conservation of energy equation that we had. If you take the traditional one and divide it by volume, you'll get this. Okay? So this is just energy per volume. All right? So the key point is, because it's conservation of energy, remember when you add up all the energy at one point in a system, and then you add it up at a later point, it always equals the same thing. So you end up with this on one side, and then another version of this on the other side. That's why it's equal to a constant. Okay? So the total change in energy per volume should always be the same at any given point for a closed system. Okay? So if we want to break down what's happening, let's say we have a fluid, this is just frozen in time. So exactly like what we were looking at before, okay? But if we just take a little piece of it and look at it by dissecting it, okay? So let's say we take a little chunk over here and a little chunk over here, okay? This little piece of fluid, and obviously it's hard to freeze it in real life, these both have cross-sectional areas, so you can see how this might go together with another equation we just learned, the continuity equation, okay? So here's a force here, and remember, force is pressure times area, because pressure is force over area, okay? Here's the force coming in over here. This is pressure 1 times area 1. Okay, so force 1 is pressure 1 times area 1. Force 2 is pressure 2 times area 2. Here are your speeds. This is velocity 1. This is velocity 2. Okay? And here's our change in height. Okay? So remember, if we go up, then we gain gravitational potential energy. If we go down, we're changing that gravitational potential energy into kinetic energy. Okay? So why do we store water above ground? Yeah, we're storing gravitational potential energy, so when you want to send the water somewhere, you already have stored the energy by putting it at a particular height. Okay? So let's just talk about what happens in the special cases, so whenever we're not using certain terms. So for instance, if speed is constant, this term goes away, because if you have this term on both sides of the equation, it will cancel. Okay, so let's talk about applications. This is why water, I asked this prematurely, this is why water is stored in towers, okay? If you have something above, actually this isn't a water tower, this is a joke. If you've ever been to Seal Beach, somebody's house that they made to look like a water tower. Or it was a water tower that someone turned into a house. I'm not sure which order it went in, but it is very distinctive. I think you could rent it on Airbnb. Yeah.
It looked like Morgantown for a second. I was like, wow.
This is very impractical.
That's why they hire people, dog.
Yeah, I'm pretty sure they're not poor because they have a really good view of the ocean. So, okay. But this is why water is stored in water towers. You can use the potential energy from gravity to create kinetic energy, which means water flow, okay, or any kind of fluid. If we have a constant y, that means everything's happening at the same height. We're not using gravitational potential energy, okay? This is a situation where you can change pressure by changing the cross-sectional area. Another application of this is, have you ever opened the window of your car on the freeway?
Yeah.
Yep.
Okay, what happens? Well, actually, that's a resonant frequency thing. But what else happens?
All your receipts get sucked out of your
Yeah,
Yes.
that's right.
Things get sucked out. What about ears? How do your ears feel?
pop.
Sometimes they pop, right? When do your ears normally pop?
I'll change
A change in pressure. So when you change elevation, you change where you are in the gauge pressure of the atmosphere, right? You change pressure, your ears pop, right? If you go underwater, you change pressure because you're going deeper into a fluid. That means your ears pop. So if you're opening the window and your ears pop, that means you haven't changed elevation. You haven't changed where you are in the fluid that you're in.
Just change the pressure.
But you changed the speed, right? So what's the speed of the air relative to you in the car usually?
Miles per hour, whatever you're driving.
Mostly zero, right? If you're in the car with all the windows closed, is the air moving relative?
No.
Well, if you've got the air conditioner blasting, maybe
Right.
it's moving a little bit. But
Do we
since
open 2 windows or just 1 window?
it doesn't actually matter for this
Because like if we open 2 windows, then you get flow through the car. I always thought that like if you open 1 window, you like pulled a vacuum, and that's why.
Yes. But turns out it works. Okay. Well, that gets complicated. But essentially, if you open 1 or 2 windows, you have fluid flowing past your car at a higher speed.
Yes.
Okay? So if it's going at a higher speed than the fluid in your car, that changes the pressure. Okay? Because higher speed means lower pressure. Okay? So that means air is going to start flowing. It does create like sort of like a vacuum. It sucks air out of the car.
It's the same principle as like airfoils, though.
Yeah.
That's why you have like greater velocity underneath a wing or above a wing, so you pull it vacuum above it.
In a very, yes. This actually is the same way that we describe how airplane wings work and how lift works, although that's not 100% true, it turns out. But we'll talk about that in a little bit of detail. But yes, if you have a different velocity on one side of something than the other of the fluid flow, you will create a pressure difference. Okay? And so your ears will pop. That's the evidence. Things like this can also happen. So for instance, if you are in a house, what speed is the air moving?
Whatever.
Pretty much
Relative
zero-ish, approximately 0, inside your house.
Idealistic,
There could be some flow going around the house, but it's not moving very fast.
idealistic 0.
If you have a lot of wind going over the top of your house, like for instance, it's a hurricane, okay? That means that you have a high velocity above the roof and a low velocity below the roof, and that means there's a pressure difference on both sides of your roof. And this is
It's a wind shear.
sort of the
Opened it like a can.
Dude, that's how you get like a full house vacuum.
weather caught on
Yeah.
camera.
That's pretty funny.
I think there's sound. Hang on.
They're all screaming.
They're like, open the window. Never mind.
He's like, it's kind of freezing.
So if you had opened a window and then kept your roof
They do a lot of work.
Wouldn't it pass through the house instead then?
You'd be able to open a few windows.
word-
'Cause you have to
If
get
I
it
open
fast
all the
enough
windows.
flow through your house. And that might lead to different damage, where the 100-mile-an-hour wind is now just racing through your house. So you won't lose your roof, but a lot of other things might get messed
you might
up.
destroy all your belongings.
Yeah.
Yeah.
That's
Maybe your
fine.
cats.
Your cat. So,
It's
yes.
the same thing. We had to open windows in tornadoes back east. It was the same thing. They would have us open the windows right before the tornado to create the pressure difference because the pressures are.
Yeah, well, it will reduce the pressure difference, and it might be enough to reduce the amount of force so that your roof stays on a little bit
I know,
longer.
really weird.
A little long.
So, faster moving fluid means lower pressure essentially. So if you can change the fluid flow on 2 sides of something, that can be bad, like in the situation we just witnessed, okay, where your roof flies off because there's now a force pointing up and it gets some nice aerodynamic lift like an airplane in a situation where you don't want to fly. There's some fun applications of this, like this. Okay? In sports, we use this differential in fluid flow to create spin, right? So a curveball would be an application of what you could use this for. If you play soccer, you can create spin. It actually works really well in golf. There's a reason golf and tennis, those balls have texture so that they can actually accentuate this fluid flow change because in the stupidest explanation, the furry part of the tennis ball catches the air. Okay? But yeah, this is the reason that most balls they're not completely smooth. Okay? So like for instance, if baseball has the stitching, they could easily make baseballs that don't need stitching, but you want them to get the rotation that you can get from the. It's also easier to hold
So
because
if you made the
fingers.
stitches like more pronounced, you can technically get like a more responsive.
Yes, this is the next big scandal in the World Series, I'm sure. But and also, this is the reason that umbrellas can turn inside out. Okay, and also leads to the fun application. Mostly, this is like the biggest part of the effect of aerodynamic lift. Okay, here's a.
It's all just a lie.
Is this a video? Yeah, here's a little video on lift.
Airplanes stay in the air because of one simple fact. There is no net force on them. And with no net force, an object at rest stays at rest, and an object in motion stays that way, even if it's in midair 10 kilometers above the Earth's surface. Now, of course, it's not like there aren't forces acting on the airplane. Gravity pulls down on the plane itself, plus all of the people and baggage inside, and every single air molecule that's shot through the engines or collides with the fuselage or wings pushes on the plane as well. But if all of these forces are balanced, in particular if the air molecules push the plane up enough to counteract gravity, then the plane stays up. Getting air molecules to push the plane up is the crucial part of flying, and planes do this by making sure the undersides of the wings crash into more air molecules more violently than the upper sides. When a plane is parked on the ground, air molecules bounce off of the top and bottom of the wings in roughly equal amounts, or with equal pressure, and no lift. But in motion, the curved shape of the wings and their slightly inclined angle means that the bottoms smash into more air molecules than before, and smash harder into those molecules, so the pressure on the bottom of the wing goes up. In addition, fewer air molecules now strike the top of the wing, and those that do strike it less forcefully, partly because it's being shielded by its own forward motion, the way running into the rain keeps your back drier, and partly because a curving stream of air has lower pressure on the inside of the curve since the molecules get thrown centripetally to the outside. But whatever the reasons, the pressure on the top of the wing goes down. So low pressure or less downward force on the top, plus high pressure or more upward force on the bottom, and the plane has lift. And if the force imbalance is big enough, it can lift the plane up into the air against gravity. Now, all this crashing into air molecules to lift the plane also pushes to slow the plane down, which it would if not for engines. Engines also push air, in this case backwards, either via a propeller or a jet driving a propeller. For various reasons, it turns out that you want to have a really big propeller driven by a really small jet for the most efficient engine. But even in inefficient engines, the spinning fan blades generate their thrust, which is essentially horizontal lift, by moving quickly through the air with a curved shape and a slightly inclined angle. They're essentially mini wings. And so an airplane is essentially a meta wing. It flies by moving mini wings fast enough to push air molecules backwards, which moves the plane forwards fast enough that its big wings push air molecules down. Whoa. Wingception. I'd like to say a big thank you to Airbus for sponsoring this Minute Physics video. Airbus brought me to their production facilities in Europe to see how they make the new Airbus A350 airplane. Here it is. It is an incredibly cool and big airplane, and I made a video about how they make it, so you should go check that out. It is pretty incredible. Also, the engines on the thing are so enormous. You really can't tell from a model like this, but when you're there in person, it's just astounding, and that is precisely so that the engines are more efficient. As I explained in this video, if you have a big fan on an engine and a small jet, they will be more efficient, and that is how this airplane is one of the most efficient ones in the world at this point in time. So again, thank you to Airbus for supporting this video. I hope you enjoyed it.
Something. So in physics, this has bothered me for years. We always say like, oh, Bernoulli's equation is why airplanes fly, but it's not completely the whole picture. That was the whole picture in simple terms. So yes, like to the first order, like to the first simplest model, Bernoulli's equation contributes. You do get the whole idea is to get a pressure differential by having different speeds, but there's a little bit more to it than that because the shape of the wing matters a lot, and like they said, the angle of attack, the camber, all of that stuff creates, it's more than Bernoulli's equation, as you can see, because the density of the air molecules is significantly lower above the wing, and that's a better, more satisfying explanation. Otherwise, it's like wizardry. So, okay, what?
It hurts your feelings less.
Yeah. Let's talk about the Magnus effect with these guys from.
We're here at the Gordon Dam, and what we're going to do is demonstrate from the very top the effect of spin on a ball. So we're going to get a basketball and drop it from 140 meters up, one without spin and one with spin, and see what happens.
All right, you guys good down the bottom? Yeah, thank you. We're watching.
Ready? Yeah, so it's crazy, just dropping it with no spin or anything like that, and as you could see, you know, the ball was sort of doing a sway thing, so it wasn't going directly straight. It was pretty hard to predict where it was falling, so that was really cool. Ready? that go!
That's incredible.
So you want those to get back in the water, do you?
This is Brett who just threw it. I literally just dropped it with a bit of spin, like I didn't even throw it, and it just took off. Like we had no idea that was going to do that.
But yes, in the water, please.
So that was a pretty amazing experiment with some really interesting results. So the first one that we had no spin on, it dropped straight down with some lateral movement, quite a lot of lateral movement as you would have seen, but it didn't actually go forward at all. So it was almost, fell directly below where it was dropped, which is what you would expect. But the one where we added the backspin, it went perfectly straight, but it really took off as it gained speed, and it went, close to 70 meters, I'd say, from the point at which we threw it. So 70 meters horizontally. So that was incredible. And as you can imagine, when you're doing a trick shot, all it does is highlight the complicated nature of the spin of the ball and how far it goes. If you put slightly less spin, it's going to go way shorter. If you add more, obviously it will go further. If you throw it without spin, then it's just going to fall straight down. Very interesting. We learned a lot. We were really impressed with the results, and we hope you were too.
Our good mate Derek from Veritasium has done a really cool video which explains why the ball went so far with the backspin. Watch the video and then check out and subscribe to his channel for heaps more great science videos.
Recently, some friends of mine went to the Gordon Dam in Tasmania, which is 126.5 meters or 415 feet high. Then they dropped a basketball over the edge. You can see that the basketball gets pushed around a bit by the breeze, but it lands basically right below where it was dropped. Now watch what happens when they drop another basketball, but this time with a bit of backspin.
Whoa, look at that go!
That's incredible.
So you want those to get back in the water, do you?
This is Brett who just threw it. I literally just dropped it with a bit of spin, like I didn't even throw it, and it just took off. Like we had no idea that was going to do that.
And this is where I come in. The basketball was subject to the Magnus effect, which affects all rotating balls or cylinders as they fly through the air. And it works like this. As the basketball picks up speed, air on the front side of the ball is going in the same direction as its spin, and therefore it gets dragged along with the ball and deflected back. Air on the other side is moving opposite to the ball spin, so the flow separates from the ball instead of getting deflected. The net result is the ball pushes air one way, so the air applies an equal force on the ball the other way. And this is known as the Magnus effect, named after Heinrich Gustav Magnus, who described it in 1852. Of course, Isaac Newton beat him to it by nearly 200 years, describing the flight of tennis balls at Cambridge College. But, he's got enough stuff named after him. This effect is very important in sports like tennis, soccer, and golf. But could it have non-sport applications? Perhaps. This is a sailboat. I know it doesn't look like a sailboat, but those aren't chimneys. They are spinning cylinders called Flettner rotors, and they take the place of the sails. They deflect crosswinds using the Magnus effect to propel the ship forwards. And this is a plane with spinning cylinders instead of wings. Using the Magnus effect, the cylinders actually generate more lift than traditional wings. However, they also generate way more drag, making them impractical. This plane only flew once, and then it crashed. But the Magnus effect is making a comeback. Here is an experimental rotor wing aircraft, which generates all its lift from spinning cylinders. And this is the E-Ship 1, which uses 4 spinning cylinders, that's 4 Flettner rotors, to increase its efficiency and reduce the amount of diesel it burns. So in the future, the Magnus effect may help more than just basketballs fly.
Oh, look at that go!
Now the real reason my friends from How Ridiculous were at the dam was to set the world record for the highest basket ever scored. So go check out their channel and the video and subscribe to them for more epic trick shots.
We're gonna take a break. Then we're gonna come back. Answer. Actually, no. We're gonna finish this. We only have 3 more slides. Let's do that. Sorry. Okay. Let's discuss this and vote again. Now remember, this is the liquid. So if it's higher up, what does that mean about the pressure?
More or less pressure.
On the side.
Oh, I rigged it back.
Wait, so is the light colored thing the air? Is that what that's supposed to be?
Yes.
I'm
Oh.
not understanding this.
Dark thing, liquid.
Yeah.
Light thing,
Ah.
air.
Okay.
It's a very confusing visual.
Down.
Oh.
Oh, wow. Wow. Yep, the answer's B. You guys are killing it. So, once you know which thing's which, that means if you have a fluid going higher, there's less pressure there, which means it's more like a vacuum. It's sucking the fluid up that way, right? More pressure means it's pressing the fluid down. So this would have the least pressure. This would have the most pressure. This would be right in between. That's answer B. Okay? You want to try? Actually, you guys got this pretty well. You don't have to do this. Oh, there's a whole problem. You guys want to do this problem?
No.
Okay.
Okay guys, so here we're trying to figure out a pressure difference, but we're really only given two speeds. So over the top of the wing we get this speed, and across the bottom of the wing we get this speed, and we know the density. So let's think about for part A, Bernoulli's equation looks like this: P1 plus 1/2 rho V1 squared plus rho GY1 is equal to P2 plus 1/2 rho V2 squared plus rho GY2. Now, one thing you'll want to notice is between the top and bottom of the wing, this difference in y is going to be pretty small. And you can actually plug it in. You could assume the wing is like a meter, and you'll find that the value that adds to the final answer is like less than 1%. So we're going to start by just assuming that we can ignore these terms because the wing is so thin. The next thing we want to notice is that we want the difference between P1 and P2. So we want an answer that looks like delta P, which should be P1 minus P2. So if we rearrange this equation, we're going to end up with 1/2 rho, and that's going to be 1/2 rho V2 squared minus 1/2 rho V1 squared, which you can rewrite to say 1/2 rho V2 squared minus V1 squared. Okay? Now, we want this to be a difference, and basically, however you write it, it's positive if you choose V2 to be the bigger number. So we're just looking for an absolute difference. That means we can take the absolute difference of this, and that's 1/2 times 1.3 kilograms per meter cubed. And then this is going to be 250 meters per second squared minus 220 meters per second squared. So when you add all this together, you end up with a pressure of 9,165 newtons per meter squared. Okay, so that's our change in pressure, which we got from Bernoulli's equation and using only the two velocities and the density of the air. All right, so that's part A. For part B, we want to know if the area of the two wings of the airplane is 10 meters squared, what is the upward force? Well, remember, pressure is equal to force over area, which means that force is equal to pressure times area. Well, up here, we already got the pressure, so all we're doing is taking that, 9,165 newtons per meter squared, and then multiplying it by the 10 meters squared of wingspan, and that's going to give us 91,650 newtons. Okay, so this is the amount of pressure. Now for some scale, if we convert this force to pounds, we can get an upward force of about 20,000 pounds. So let's just hope the plane and all the things on it weigh less than 20,000 pounds, and then we're in good shape.